Okay, perfect. So first of all, thanks for having me here today. I'm really looking forward to give this presentation. And I'm also very excited about everything that we've heard already. I think I will touch on a couple of those points. We'll talk about foundation models. We are working on foundation models for Earth observation and for weather modeling. And I want to give you a quick overview on what we're doing, perhaps a bit more in detail on the architecture side. But first of all, I want to tell you that we are not only working on this, so we are actually trying to work on specific problems people have. So we are actually targeting climate applications, and foundation models are one way for us to hopefully help to better solve those problems with climate applications. And obviously we need the computational systems for that as well, which is for us the geospatial discovery network. As I said, I will be talking about foundation models, but that's only one part of what we're doing at IBM Research. And actually, obviously, that's not only me and not only the guys sitting in Zurich, but there are many people around the globe. So we have in total roughly 3,000 researchers. And you see the green dots, that's everywhere where people are working on climate and sustainability. So typically we say that the sun never sets in IBM Research because someone's up all the time working on those models. And I think probably it makes sense to introduce foundation models a bit formally in the beginning of this talk so that we know what the differences are, for example, to numerical weather predictions, but also forecast emulators. So essentially, we have been seeing that like way back, people have been working on expert systems. They were not infusing data. They came up with a couple of rules and were applying them to data to come up with a decision. Then we moved on to machine learning. We essentially infused data, and the machine learning model was tasked to retrieve the rules itself. With more labeled data and a bit more compute, we ended up in the era of deep learning, and now we are entering the era of foundation models, where essentially the changing paradigm is self-supervision at scale. So that's what's different. Now, we already heard that this is resource intensive. So it's taken a lot of compute, it's taking or requiring a lot of data. And I just want to exemplify how we could pre-train, fine-tune, and infer with foundation models with an example, but it's not specific to Earth observation necessarily. Essentially, it's about gathering a lot of data, but as we heard in, for example, Hannah's talk, we have so much data that we cannot use all of that. It will be just not efficient enough, so we will always have this trade-off between the costs and the amount of data. So what we need to do is we need to come up with a sampling strategy that allows us to gather the, let's say, right amount of data in a high quality way so that we avoid just training for the sake of training on very large scale data sets. When we've done that, we probably want to filter out and pre-process the data so that we even enhance the quality in the data set that we have. And then we end up in the self-supervision part, where people are working with masked image modeling, for example, or contrastive learning. Essentially, we want to guide the model itself based on the data that we have to avoid labeling in general. And this will hopefully bring us to a good encoder that allows us to encode the data that we have to have an abstract representation of the data, and use that in the next step in the fine-tuning to solve specific tasks. And actually, we already heard about this. We already heard that for fine-tuning, we still need labeled data, right? Our idea is just, it would be good that we don't require to have 15,000 images of floods, but perhaps more like 20 images. And the pre-training that was way more general and not flood-specific essentially facilitates this step. And finally, obviously, we want to infer with these models, so we want to use them in applications. That's already a bit up in the cycle that we've seen before, so that's more in the climate application part. And essentially, we want to use the weights that we obtained from pre-training and fine-tuning during the inference to solve specific tasks. For example, the burn scar example that Manil showed. That's exactly what we've been doing with NASA in our collaboration on geospatial foundation models. Essentially, we use a lot of satellite images. We use the HLS product for that. And just as an example, from Sentinel-2, it would be 3.5 terabyte a day. HLS builds up on Sentinel. It combines Landsat 8 and Sentinel-2. So this is just to give you a rough estimate of how much data we have and how important it is to not use all of it. If we train, for example, on a total of 1 year, that would be just too much data. And I mean, obviously, we want to solve a couple of downstream tasks then. For example, it might be biomass estimation or flood and fire mapping. Cool. I mean, I believe many of you know the HLS product. We've been using this for pre-training. It's at 30-meter resolution. We were using 1 year of data, and one tile covers approximately 110 to 110 kilometers. So that's what we had in the beginning. And this is a simple first version that we've been working on. Essentially, it's a vision transformer. And the idea of the model is to mask out certain patches in the input, and the model has to reconstruct those patches. So the task of the model is to understand the structure of the image, to hopefully get an understanding about the representation of the Earth, like how does Earth's surface look like. And if we do that, we are not doing that only for RGB. For example, we're doing that across several spectral bands, and we also do it across time. So we are typically infusing 3 different time steps. That allows us to get a certain notion of how does Earth change over time. So that's the general idea in the first version of this model, which is a VIT version that uses a couple of modifications for this specific task. For the initial model, we've been training on the US. At the moment, we are extending this to a global pre-training. So in the right, you see how we try to come up with a sampling strategy across the globe, because, I mean, as you can imagine, it's really difficult to have a uniform distribution. So we first need to come up with some statistics that allow us to understand which regions are similar, and then we can come up with a sampling strategy that allows us to uniformly distribute so that we are not under or over-representing certain areas in the world. So that's what we see in the right. What we see in the left is what we do with images in the pre-processing. And essentially, our idea is there are obviously a couple of patches that are missing, so we want to remove those from the data. And there are a couple of patches that are cloudy. And it's really difficult to deal with cloud data. I believe many of you probably know when you're working with deep learning and Earth observation data, cloud data is important, but typically models, at least in masked image modeling, get confused by those. They just try to predict essentially in the reconstruction that everything is a cloud. If you have a good load of cloud contamination in the training data, that's just a good guess. So the model typically seems to end up in a local minimum. So we remove a lot of that cloud data. When training on this data, we end up with a model that we have made publicly available on Hugging Face. So this is the first version of our model, where also we published a preprint on. Essentially, you see in the top that was what we had as the original image. In the middle, that was the reconstruction, that was just the masked version of the image that we use as an input. And in the bottom line, that's what our model reconstructs. So we see that the model gets a certain notion of the Earth's surface, and even by masking out 90% of the image, the model is able to reconstruct most of it in a bit of a more blurry structure than the original image, but still very good. And with this pre-trained model, we hope to facilitate solving different tasks. So we are not training a single model for example, burn scars detection and another model for land use, land change. But we are using the same model, and we just plug in different heads to the model that are specific to solving a downstream task, and we fine-tune it with very few samples, which we will see at the example of flood mapping. We have talked a lot about floods in the previous presentations. Sorry to bore you shortly before lunch, but this will be about flood mapping as well, as at least in this small example. Essentially, we saw in the figures on the right, the middle one is essentially the acceleration in the fine-tuning performance. And we see that when we do pre-training, we converge a lot faster. So we are starting already from a pretty high level of performance, and the convergence is we achieve that really fast compared to, for example, using a not pre-trained version of the model. On the right, we see the performance that we achieve when we reduce the amount of data and fine-tuning. So if we train on all the labeled data that we have from this specific flood data set, which is 252 images, we end up with a certain level of performance around IOU, which is the metric that we're measuring, of 82%. And if we reduce that by more than 80% to 32 images, we still end up in this ballpark. It might be slightly worse, but in general, it means that we can facilitate this task with less labeled data, which is one of the key differentiations that we want to see. So we have an acceleration in fine-tuning. We have the quite decent performance in terms of data efficiency. And then the third one is we are interested in whether our model generalizes well. And actually, this is what we see in the table on the bottom, and it's not something that we have been evaluating, but that's from the community. So I believe this is from Wen Lee's group. And essentially, what they did was comparing how the model performs in unseen geographical regions, and they realized that our model is quite good in generalizing, while obviously when you train very specific models like UNets for a very specific task, that might give you a good performance on the scene regions. So I'm not saying that foundation models make the claim that they are more accurate than any other model architecture, but they have a couple of cool properties like being data efficient, accelerating the fine-tuning, and they seem to generalize quite well. Obviously, we are a company and we are interested in applications. Now we are moving a bit away from foundation models to the applications. We have built a couple of tools that allow people to assess the impact, for example, of floods. So this is a flood prediction, and we compute impact maps on top of that that allow us to understand which regions are affected, and are those building areas, are those crops, are those forests. This is an example for flood in France, I believe, and the next one that we'll see is the example of burn scars in Greece. So there was a major wildfire, and essentially when we turn on the model prediction and the impact, we see which forestry areas were affected by this wildfire. Many people are interested in above-ground biomass estimation. It's an incredibly hard problem because you have very sparse measurements. And we were trying to see how the foundation model performs on that as well. So essentially what you see in the left is the actual measurements that we get. So we get very sparse measurements. There are 600 meters in between the measurements. And around, like, one measurement is only around 25 to 25 meters. So that's a super sparse problem. But essentially, our goal would be to fill in the blanks between those measurements. So we want to have a dense prediction for a very sparse problem, which is quite challenging. And I will show you one example of how the foundation model performs here. Essentially, we can turn on the change detection, and it allows us to understand where was where was reforestation, where did the forest go back, which we see in the red here. And essentially, we see that the total amount of deforested area was smaller than the amount that was reforested. And apart from that, we can, for example, calculate the carbon emissions and the carbon storage that this forest and the reforestation allows us to store in this area. So those are a couple of applications, and I think the important point to stress here is we didn't have to retrain our model for all of those applications. We pre-trained it once, and then we fine-tuned it to the specific tasks based on very few observations, and we saw that the model allowed us to get a decent performance on all of those different tasks, even though one is segmentation, the other one is regression. So this doesn't really matter for the pre-training. It's just a matter of how you fine-tune the models. You use just different heads to the model that allow you to solve those specific tasks. But this is not where foundation model ends, it's more where foundation model starts. So I would say that this is just the peak of the iceberg. We have just like a small proof of concept that foundation models might be something worth exploring. And now we need to think about, as Hannah mentioned, there shouldn't be one foundation model every week. There shouldn't be a foundation model for every satellite. Probably we need a foundation model that includes information from different satellites and probably also hyperspectral data. And this is what we're doing in a project together with ESA in that case. So, for example, our idea is to encode information from different satellites and then later fuse it so that we can leverage, for example, radar data along optical data, which is currently a bottleneck in foundation modeling. So we are working on different approaches how we can get there, but essentially the bottom line is we probably don't want to have a foundation model for every satellite, but we want to have foundation models that include information from multiple satellites. So that, for example, if we have cloudy data, we don't need the optical part, we just use the radar part, and vice versa. In this project, we are not only looking into multi-satellite, but also multimodality. This is something people are very interested in at the moment in general, I believe. At least since the release of GPT-4, everyone wants to do multimodality. And there are probably a couple of cool cases for Earth observation as well. So for example, we are looking into how we can query a model based on text that gives us back images that hopefully match the textual image, the textual caption that we pass to the model. So in this case, it will be we query the model for flooding in suburban areas, and hopefully it will give us something back like what we see on the upper right. What we have to do for that, I mean, that's probably an open research question, but one approach might be something which is similar to the clip approach. So essentially the idea is you not only encode the image, you also encode appropriate textual captions of this image. And by encoding both of them and comparing their embeddings, you hopefully end up with a representation that puts the caption and the corresponding image very close together, so that when you enter a textual caption during inference, you hopefully will get out an image that is very close in the embedding space. Besides those two topics, we believe that foundation models can be used for very different kinds of applications. We have now been talking about how we can retrieve data with foundation models, how we can segment images, identify natural hazards, measure above ground biomass estimation. But maybe there are applications that are more, let's say they are less obvious. For example, at the moment, data from different satellite missions are stored across the globe on in different services with different data providers. And our idea is essentially we might want to use foundation models to compress all this information that we have at a data provider so that people that want to make use of the data don't have to download everything, like don't download the raw data to solve a problem, but maybe we want to download the embedding. So we have a foundation model at each of those data providers that allows us to encode the data and compress it. And then we don't ship the raw data, but we ship the compressed version of it. And the data consumer essentially only has to do the fine-tuning based on the compressed embedding. So in our foundation model world, that would mean we have the encoder with the data provider, the decoder as at the data consumer, and we are exploring this in an EU Horizon project to which degree this might work and this might reduce the bandwidth, because there's a lot of energy consumption involved with downloading huge amounts of data. And we are hoping to reduce that by using foundation models to encode these large data sources. So to sum up on the Earth observation part, there are a couple of benefits that we could already identify. It's, for example, they are highly computational efficient in the sense of during fine-tuning, using those models very often makes them computationally efficient. So the pre-training is very intensive. That's more intense than doing deep learning in the traditional way. But having a single model and solving different downstream tasks with it multiple times with less data, that's compute efficient. Then we have the data efficiency part. We have been seeing that across a couple of downstream tasks, that when we're using smaller amounts of data, we still end up with a similar level of performance. The accuracy is comparable with the state of the art in other deep learning models, and we have a good generalizability to other geographical regions. However, as I said, that's more the peak of the iceberg, and we have to do a lot of more work. For example, global pre-training, working on involving cloud data, which gives us headache most of the time at the moment, and working on some architectural enhancements such as multi-satellite, multimodality, or compression. Okay. I don't think that I have too much time anymore, so I will make this quick for lunch. I want to talk a bit about numerical weather prediction and how foundation models can help there. So essentially, we have been seeing also in the other talks that numerical weather prediction has seen a revolution, and AI can help a lot in numerical weather prediction, essentially based on forecast emulators. So it's quite fast to do that. It requires much less code, and people are very interested in using AI for weather forecasting. Very high-level overview on how that works. It's just supervised learning, right? You have an input, you have a target, you produce an output with your model, and you have a loss that tries to clip them together so that the output and the target are most close to each other. That's the training signal that you propagate back to the model. During inference, it's just an autoregressive rollout. So essentially, you do your forecast based on your supervised model. And we believe that a foundation model for weather modeling should not only be that. It should not be a forecast emulator. It's not only about forecasting, right? Forecasting is essentially a supervised task. And we said that a foundation model would be a self-supervised model. So essentially, we want to combine those two worlds. So we want to recover missing information, and we also want to have kind of an emulation of the physical processes in the atmosphere. And that brings us to the foundation model. So essentially, what training a foundation model for weather should look like is something like this. We have the input, where a lot of the actual input is masked, so similar to Earth observation example. And then on the output side, we don't want to reconstruct what we have for the existing time step, but probably more something that is in the past. We already heard from Noel, that's really difficult as well. The present image and also forecast in the future. So we have this combination of reconstructing missing information, but also emulating the processes that we see in the atmosphere. This hopefully will allow us not only to do forecasting, but also to achieve other different tasks. So as with the foundation model for Earth observation, we are hoping not to only solve the forecasting problem to a certain degree, but also, for example, data assimilation or the detection of extreme weather events. And there are a couple of benefits involved with that are very similar to what we know from Earth observation. So essentially, we hope to see that we are more flexible with those data sources. We have a higher data efficiency, and the accuracy is on a high level. first one is actually an example that I wanted to show. Can I do that still? I'm not sure when. Okay. It will take 5 minutes probably. So we will talk a bit about the first one, the flexibility for data sources. Essentially, our idea is, at the moment, we have forecast emulators. So that's what we see on the top. We have a model that's trained on ERA 5, and we use the model to forecast what's the atmosphere looking like tomorrow in terms of the weather. And at the moment, I mean, that's specific to ERA 5, right? That's a data set for weather modeling, and we probably can only use it for ERA 5. Now we're interested in whether we can use such a model for other data sets as well. So there are a couple of data sets out there for weather forecasting and for the emulation of weather processes, and one of them is MERA2. All forecast models obviously would fail at this task, right? You cannot use a model input ERA 5 data and let it forecast MERA2. That's just not possible. It's not the task of the model. And with this simple example, we want to see whether if we plug in an encoder and a decoder around the model, it's possible to achieve a performance that is on a certain level that allows us essentially to use MERA2 data to forecast what the world would look like in MERA2 data tomorrow. And when we do that, based on a very simple architecture, I mean, we just use 2 layers of convolutions, so a very simple architecture, it's quite vanilla. And we use our pre-trained model in the middle. Then we see that actually we are already quite close to what we get when we train from scratch. So the red line here is what we get when we train on random weights. And the blue line is what we get when we train with the weights that we've been pre-training on ERA 5. So essentially this means that we can close the gap based on pre-training essentially by almost 30% in that example. And it allows us to make use of pre-trained models that we couldn't harness before. So before, this model was specific to a certain data set and it could not be used to other ones. Now we have a certain notion of flexibility and transferability of those pre-trained models to other data sets. Yeah, we saw that across a couple of metrics. I don't want to bore you with that, but I think this is really important. Essentially, with those stars, we denote the state of the art on ERA 5. And we, for example, see GraphCast, but also other models by NVIDIA and Huawei. And we see that when we do our fine-tuned version of the model, we can come in a similar ballpark just by using a couple of GPU hours on a single node. And this is quite cool because essentially it allows us to use pre-trained models, wrap around an encoder and a decoder in a very simple way, just for the sake of the proof of the concept. And we already end up in this ballpark. So it means that there is a certain rationale why we should do foundation modeling for weather and not just do forecast emulation. Because we not only can use it for a single data set, but we can use it across different data sets, which wasn't possible before. Yeah, this ends up with some nice figures, but probably we all want to go for lunch, so let's wrap it up quickly. Foundation models for weather modeling, we have seen that an AI in general enables weather forecasting, but that's a supervised task. And if we want to do self-supervision, we have to do something different. And our early experiments showed that this is possible to a certain degree. So we have this flexibility in foundation modeling approaches to other data sets. We're working a lot on that at the moment. Unfortunately, nothing is meant to be shown here already, but hopefully in a couple of weeks or months. And then we hope to improve the flexibility, the efficiency, and the applicability to a broad range of tasks. So that's it. We have a couple of open positions in this respect. If you're interested in that, please feel free to reach out, internships and thesis positions. And there are a couple of new papers on the applications of foundation models for Earth observation if you're interested in that. And with that, let's head off to a couple of questions and then to lunch. Okay.
Okay, yeah, we have time for maybe 1 or 2 questions, but I guess you will be also very happy to answer questions during lunch. But yeah, Tom.
Yeah, thank you for the nice talk. I was wondering if there's a specific reason that you chose a mask autoencoder and not any of those contrastive learning approaches for your foundation model.
That's a huge debate and a very good question. Paradigms in self-supervision, which is masked image modeling, what we are doing, and contrastive learning, where you compare 2 images to each other and tell the model whether they look similar or not. Both are self-supervised, but essentially they are different in the task of the model, and they have different properties during fine-tuning. It's always about how much data can you use, how big can you make your model, and when you mask out patches, you reduce your data by 90%, right? So when we only feed in 10% of the input data due to the masking, we allow for slightly bigger, larger amounts of data, but also bigger models. So that's the reason why most people go with masked image modeling. But I mean, it's an open question whether this is the best approach, and it might be that contrastive learning is very well suited for a set of downstream applications. So many researchers should work on that.
Okay, thank you very much. There's one more question.
It's great that there are a couple of questions. Then it's not me that delays lunch. Then we're all together.
Okay, I'll try to keep it short. Thanks a lot for the great presentation. I just wanted to ask, maybe you can expand on the statement that you made about foundation models with multi-source data, let's say sentinels plus hyperspectral. Can you give a bit of an indication how feasible it is, and when, timeline-wise, when can we see something good? Because everyone who sits in this room and worked with sentinels and Nmap, for example, which comes, probably knows that, I mean, there is a lot to do till these data are harmonized and usable together.
Yeah. So as many people in the room then, we are interested in that as well. I probably am not the right person to talk about the timeline, but essentially it's very difficult to fuse those different data sets in a way that we can pre-train on all of them. And there are many open questions in the pre-training scheme, whether, like, for example, how would we deal with the situation during fine-tuning when we only have available a couple of the sensors, but not all of them? So we need to come up with masking out entire channels and entire satellites during pre-training. And there's not much work on that because I believe for all other research groups working on masked image modeling on RGB images, that's not a problem. You never have this issue with missing sensors and aligning them. So it's very messy in the data. So that's what we are working on at the moment mainly. And I mean, those projects that we are working in together with ESA in that case is for a duration of 2 to 3 years. So that's a very rough timeline in which we are working on that. But I believe that there are many people interested in it and excited to see the new architectures on